Hello everyone, welcome back to another video for heat and mass transfer. So this is going to be for homework 3 part B. This homework is going to be talking about the Nusselt number, which is a very specific dimensionless number that relates to how something is flowing across a flat surface. So I've just written, my pages are blank. I've just written that we are talking about the Nusselt number today, which is this value here. So Nusselt, if you're analyzing this in the x direction, which is what we'll denote that as, it's 0.332 Reynolds number in the x direction to the half power, which is just square root, times the PR Prusselt number, I think. PR is actually the Prandtl number. I got that wrong. Prandtl number to the 1/3 or cube root of that number. And so the Nusselt number, like I said, is going to be describing a system where you're going to see flow across a flat laminar surface. So for example, we'd just be looking at this flat plane surface, just a plane. And if you were looking at this from the side view in the increasing x direction, you would see some sort of boundary layer form across that surface. So if we're looking at this surface from the side, that's the sort of boundary layer that we're forming. So we have heard of boundary layers before many times in fluids. Sorry. I was drawing the arrows. That bottom arrow is kind of janky, don't mind it. Yeah, so it's going to form some sort of boundary layer as we see the flow across the surface of this plane. And so the flow is going to be going, the plane is right here, and the flow is going to be going across this way. So then as it goes across the plate, we see that boundary layer form to reach some sort of top crest where that delta is going to be the distance between the top of the boundary layer and the surface that we're going across. So that's when your flow begins to level out in the boundary layer. But the way that we find Nusselt number is it's going to be some sort of ratio between conductive and convective forces. So Nusselt is describing the heat transfer, the heat flow across this plane with the boundary layer. But since there is one point where you're in contact with a surface, that's going to be conductive because it's between two materials. And then when the flow is just up and exposed to the air where it's not touching the surface of the plane, that's going to be our convective forces. So that's why it's going to be a ratio between the two, because both of them are acting on this. So we can write this. So I just wrote down here, ratio between conductive and convective forces. So we can write this ratio as the convective force is going to be in the numerator. So that's going to be H. So if you recall back to our flux, when we learned about flux for convective and conductive forces, we know that for convective forces, that's equal to the HA, DT, etc., that equation. So H corresponds to our convective coefficient. And then on the bottom of that is going to be K, because that corresponds to our conductive forces. So K is the conductive force coefficient from Fourier's law, as we remember. And then that is going to be multiplied by L, which is the total length that we're looking across this boundary layer for. So it's going to be like this total length on the bottom here of our boundary layer, that L, and that's going to be the ratio that we have here. The convective force on the numerator, conductive in the denominator, and multiplied by the total length. So just to reiterate here, I'm going to say this is convective, over conductive is what we have here. So then that's part of our ratio first, and now we're going to look at the units of Reynolds number, which is also a part of Nusselt number. So we can recall that Reynolds number is rho v d over mu. And so we have rho v. Instead of d, I'm going to put L because we have dedicated L as being the length unit in our system. So that will substitute in for d just for consistency amongst variables. So rho v L over mu. And that is our units for Reynolds number, as we recall. And then for Prandtl's number, we can see that Prandtl's number is about momentum, diffusivity over thermal diffusivity. So we can recall that for thermal diffusivity, we use K in order to define that. But we need to get K in the correct units of diffusivity rather than conductivity, because right now K is our thermal conductivity coefficient. And in order to get it into diffusivity, we're going to have to divide that by our heat capacity and our density. We actually did solve for this a couple videos back, so if this sounds confusing and unfamiliar, then you could go back to those other videos. But that was how we changed the thermal conductivity into a diffusivity component. And then for the momentum diffusivity, you're going to have your viscosity, which is mu, but that's not in the correct units either. So in order to get that into the correct units, you have to multiply by density. So here I just have that Prandtl's number is a ratio between the momentum diffusivity and the thermal diffusivity. And then in order to get those into diffusivity units, you have to divide each of those by density, and then the thermal diffusivity one step further by dividing by heat capacity. So if you simplify that ratio, you're going to get mu times density, mu times heat capacity, over the thermal conductivity. So that's what we have for Prandtl's number. So now we can plug these units back into Nusselt's number in order to find out how we can maximize the sort of flow that we're getting across this flat surface. So now we're going to plug in all of these values that we found for everything back into the Nusselt equation. So once again, Nu x equals 0.332, Reynolds number to the 1/2, Prandtl's number to the 1/3. So for Nusselt number, we said that that's equal to the ratio between the convective and conductive forces. So for the Nusselt left side of the equation, we can plug in HL over K. So that's what we have here, HL over K. It's going to equal 0.332 times Reynolds number. So now we can plug in the units that we found for Reynolds number, which is going to be density, velocity, length, divided by mu, or viscosity to the 1/2, and then same for Prandtl's, we found that to be viscosity, heat capacity over K, and this is all raised to the 1/3 power. So that's what we have here. I just plugged in all of the units that we found earlier for each of these parts, and now we can simplify this. And so the whole point of what we're trying to do here by analyzing this is to see the best way that we could maximize however much heat transfer that we're going to have across this plate. So we're trying to see what kind of conditions should we apply in order to get the best case scenario for heat transfer. And because of this, we're going to want to look at just H, which is our convective forces. So that's how well we transfer that heat when it's going across the plate compared to the air. And we're looking at that one because that is in the numerator here. So we'll do H equals, we're going to move the K and the L on the left side of the equation over because we're evaluating for H, which is the convective coefficient. So H is going to equal 0.332, and then times, everything remains the same as before. And except this time it'll be multiplied by K over L. So we just moved the L and K over to the right side of the equation now. And now we're going to go ahead and apply those those powers to the different variables that they're being applied to simplify this a little bit farther. So then you'll have H equals 0.332. We have density will be to the 1/2, velocity will be to the 1/2. But now we have the length to the 1/2 divided by length to the first. So that means that we're going to have length to the negative 1/2 power now. So that'll be length in the denominator 1/2. And then for our mu, which is our viscosity, we'll have the denominator, so it'll be mu to the negative 1/2 times mu to the 1/3 in the numerator. So if we find common denominators there, that's essentially equivalent to mu to the negative 3/6 times mu to the 2/6. So that'll become mu to the negative or to the 1/6 power in the denominator. Okay, so now we have heat capacity to the 1/3, and we have our thermal conductivity to the 1/3 in the denominator. So thermal conductivity K to the negative 1/3 times K to the first, because that's in the numerator raised to 1 power. So that will become K in the numerator to the 2/3 power. And so this will become our new simplified powers of each of these. So density to the 1/2, velocity to the 1/2. We simplified our L from L to the positive 1/2, L to the negative 1 to be L to the negative 1/2. Heat capacity remains the same. K, we have K to the negative 1/3 in the numerator, and then, in the denominator, and then K to the first in the numerator, so K to the 2/3. And then viscosity changes to the negative 1/6 here. So now when we look at this, we have to decide which variables can we modify in order to get the best H value possible. So density cannot be varied. It just depends on what your fluid is and what your material is. Same thing with heat capacity, thermal conductivity, and viscosity. So the only things that we could really change are velocity and length. But velocity can be much harder to control in this sort of situation. So we're going to look at how the length can change how much heat transfer we get through. So the length is in the denominator to the 1/2 power. So this means that the bigger the length gets, the more we're going to divide the whole number by, which means that it's going to get smaller as the length gets bigger. So H will get smaller as L gets bigger. So that's the kind of relationship we found. Out of all the variables that we could realistically control, the length of how far it's moving across this plank, this here, as that length gets farther, the heat transfer that makes it all the way across from start to end is going to be less because it's going to be going over more length. So this means that we want to reduce as much as possible the horizontal movement that we're having, or the parallel movement, or the parallel length that we have that we're looking at. And instead, we want to maximize the perpendicular length that we're looking at, because that will make our heat transfer much more efficient, a bigger number. It will be much better for the system if we do a perpendicular sort of analysis rather than horizontal or parallel to the plane. So that's everything for Nusselt number. Hopefully that made sense. And that's it for part B.